All right, let's jump right into IP static routing. Now, this is one of those really fundamental networking concepts, but it almost immediately brings up a really big question.
I mean, think about it. We've got these incredibly smart dynamic protocols, right? Things like OSPF that can figure out the network all on their own and even reroute traffic when something breaks. So why on earth would anyone choose to manually configure a path? It just feels kind of backward, doesn't it? Well, as you're about to see, it all comes down to one word: control.
So here's the core trade-off. Dynamic routing? Yeah, it's awesome for big, messy networks because it just scales and adapts all by itself. But static routing, that gives you absolute, predictable control. You tell it where to go, and that's the end of the story, period. And that's what makes it so simple and so efficient for smaller setups, or when you have a very specific job to do.
And that quote just hits the nail on the head. You shouldn't think of static routes as some old, outdated thing. Nope. Think of them as a specialist tool. It's like a scalpel in a surgeon's hands. Let's say you need to force every single packet going to a secure server through a very specific firewall, even if the network thinks there's a shorter path. A static route is how you do that. Or what about a simple little network with only one way in or out? A single static route is just so clean, so simple. You don't need all the extra chatter from a dynamic protocol.
Okay, so how do we actually build one of these things? Let's break down the anatomy of a standard static route. When you get right down to it, it's really just about telling a packet exactly which path to take.
And we basically got three ways to do it. We can tell the router the IP address of the next router in line, we can tell it which of its own physical ports, the exit interface, to shoot the packet out of, or we can give it both. But see that little warning there next to exit interface? Pay attention to that one, because that's where the biggest, most common mistakes, the gotchas, are hiding.
Which, brings us to probably the most important part of this whole thing: the rules and the gotchas. Getting these right from the beginning will save you from some serious headaches down the line.
So let's tackle that warning right now. When is it a really bad idea to only use the exit interface? Well, it all comes down to one very specific situation, and it's all about what kind of network you're dealing with. Okay, so here's the deal. Imagine you're on a regular Ethernet network, the kind with maybe dozens of different devices all connected. If you just tell your router, hey, send this packet out of the gigabit Ethernet 0/1 port, the router's kind of left scratching its head. It knows which cable to use, sure, but it has no idea which device on that cable is the right next hop. So what does it do? It has to scream out an ARP request to figure it out, and that's just inefficient. It's extra work.
The solution? Simple. You leave absolutely nothing to chance. For any of these multi-access networks like Ethernet, the best practice, the right way to do it, is to use what's called a fully specified route. You tell the router both the exit interface and the IP address of the next hop. No guesswork, no ambiguity. It's the cleanest, most efficient way to get it done.
All right, let's switch gears to IPv6 for a second. There is one rule here that's not just a good idea, it is absolutely mandatory. If you're using a link local address as your next hop, one of those addresses that starts with FE80, you must also specify the exit interface. Why? Well, think about it. Those link local addresses are only unique on their own little segment. Your router might have 5 different interfaces, and there could be a device with the same FE80 address on each one. You have to tell the router which link you're talking about.
Okay, so we've got the standard route down. Now let's get into the really cool stuff, the specialist tools. We're going to look at default routes, floating routes, and host routes. And each one of these has a very, very specific job.
First up is the default route. You'll often hear this called the gateway of last resort, and that's exactly what it is. It's the ultimate fallback plan. If a packet shows up and the router looks at its routing table and says, I have no idea where this goes, it sends it to the default route. The classic example, your router at the edge of your network pointing all unknown traffic to your internet service provider. And a fantastic side effect of this is that it keeps your router's table super clean. It doesn't need a route for every website on the planet, right? Just one route that says send everything else that way. And you can't miss the syntax for this one. In IPv4, we call it the quad 0 route. It's just 0.0.0.0, 0.0.0.0. It matches everything because that all zero mask basically means I don't care what the destination is. For IPv6, it's the same idea, just written as /0. And a cool little tip, when you're looking at a routing table, the active default route is almost always marked with a little asterisk.
All right, next up is one of my favorite tools, because it's just so clever: the floating static route.
Now, this route doesn't handle your normal everyday traffic. No. Think of it as a pre-configured backup plan that's just floating there, inactive, waiting for the main route to fail.
So how does it work? The secret sauce is something called administrative distance, or AD for short. It's basically a trustworthiness score from 0 to 255. The lower the number, the more the router trusts that route. And here's the key part. A standard static route has a default AD of 1. That's super low, which means it's incredibly trustworthy, more so than most dynamic protocols, in fact.
So here's the trick. We set up our backup route just like any other static route, but we manually tweak the AD to be something higher, like 5 or 10. As long as that primary route with its super low AD of 1 is up and running, our backup route with an AD of 5 is completely ignored. It just floats. But the second that primary route goes down and vanishes from the routing table, bam, the router instantly activates our floating route and traffic starts flowing again. It's an automatic failover.
And finally, we've got the most precise tool in our entire toolkit, the static host route. Just like the name says, this route doesn't point to a whole network of computers. It points to one single host, one specific IP address. It's the ultimate in precision. And the way you do this is by using the most specific subnet mask you possibly can. For an IPv4 address, that's a /32 mask, or 255.255.255.255. For IPv6, it's a /128 prefix. When the router sees that, it knows this path is good for one and only one destination IP address. No ambiguity whatsoever.
All right, so we've configured our standard routes, our defaults, our backups, our host-specific paths, the whole shebang. Now, how do we actually prove they're working? Let's talk about verification, and then we'll wrap up with the key takeaways.
So you've got a few commands in your arsenal here. You can look at the routing table and filter to show just your static routes, or you can check the running config file. But you know what? All of that just shows you what you told the router to do. The real ultimate test is always connectivity. Can you actually ping that destination? Can you run a tracer and see the packets taking the exact path you wanted them to? That's the only proof that really matters.
So let's just do a quick recap of our static routing toolkit. You've got your standard route, that's the basic building block. You've got the default route, which is your catch-all path for everything else. There's the floating route, your super smart backup plan, and finally the host route, which is that precision scalpel for a single device.
And that brings me to one last thing I want you to think about. We know dynamic protocols are great for managing the big, complex network. But now that you know how this stuff works, how could you use a floating static route as a targeted manual failsafe for just one critical server, all while OSPF is handling the rest of the network? Think about that for a second. It really gets you thinking about how these two worlds, the manual and the automated, can work together, right? It's not a choice of one or the other, it's about blending them. It's about using that surgical precision of a static route to build a custom safety net exactly where you need it most, all while living inside a bigger, dynamic network. At the end of the day, it's all about using the right tool for the right job.